Welcome to this lesson on type conversions in C and C++ programming. In statistical computing, we constantly work with different types of data, like whole numbers and continuous decimals. Understanding exactly how the computer translates between these different types is absolutely critical. It ensures your mathematical calculations remain perfectly accurate and prevents catastrophic data loss in your software. To begin understanding this topic, imagine you have a small teacup filled with water and a large empty gallon bucket. If you pour the water from the teacup into the bucket, the water fits perfectly without any issues. But if you try to do the reverse and pour a completely full gallon bucket into a tiny teacup, the water will overflow and you lose a massive amount of liquid. In programming, data types like integers and decimals have different physical sizes in the computer's memory. Type conversion is the process of changing a value from one data type to another, much like moving data between different sized containers. Now that we understand what type conversion is, let us look at how the computer handles it automatically. This is called implicit type conversion or type coercion. When you mix different types in an equation, like adding a whole number and a decimal, the compiler automatically upgrades the smaller data type to the larger, more precise format. This automatic upgrade is called promotion. The computer quietly changes your data behind the scenes so that the math works out perfectly without losing any detail during the calculation. This automatic upgrade can be represented by a simple equation. Here, R represents the final result, I represents an integer, and F represents a floating point decimal. Conceptually, when the computer sees an integer and a decimal in the same operation, it knows the decimal has higher precision. So, it automatically converts the integer into a decimal before adding them together. The final result R simply adopts that higher precision automatically. For example, if I is 5 and F is 3.2, the computer turns 5 into 5.0 to keep the math perfectly accurate. Sometimes the automatic rules are not enough and you need to manually force a conversion. This is called explicit type conversion or casting. In modern C++ programming, we use a special safer operator called static cast. This is a highly visible way to convert types because it checks at compile time to ensure the conversion makes logical sense. You are giving a direct command to the computer, saying that you know exactly what you're doing and demanding that it changes the data type right now, regardless of the automatic rules. Let us look at the mathematical representation of an explicit cast. V new equals C of V old. Conceptually, the computer takes your original value, V old, and applies the strict rules of the new target type through the explicit casting function C. It then outputs the newly converted value, V new. If the target type is smaller than the original type, the value might be severely altered or chopped down to fit. As the size of the target type decreases, the risk of destroying your original data increases dramatically. Before we see an explicit cast in action, let us review the standard formula for calculating an average. A equals T divided by C. In statistical computing, you often need to divide a total sum of whole numbers by a count of items. If both variables currently hold whole numbers, the computer will perform integer division and throw away the decimal part. To get a precise decimal average, we must change one of them to a decimal to trigger automatic promotion. This is exactly where our explicit cast comes in. Let us see this with a concrete example. Suppose a student has a total score of 14 points across 4 assignments. We want to find the exact decimal average. If we simply divide the integer 14 by the integer 4, the computer gives us 3 instead of 3.5. To fix this, we explicitly cast the total score, 14, into a floating point number using the static cast approach. This forces the computer to treat the top number as the decimal 14.0, setting up our equation correctly. Now that we have successfully converted the top number, we are dividing a decimal by an integer. Because the top number is now a decimal, the computer's implicit conversion rules kick in. It automatically promotes the bottom integer 4 into a decimal 4.0 so that both sides match. Both sides now have the exact same level of precision. The division can now proceed without dropping any fractions, ensuring our math is handled correctly and no data is lost in the intermediate steps. With both numbers promoted to decimals, the final division is performed accurately. 14.0 divided by 4.0 yields exactly 3.5. By using an explicit cast on just one number, we triggered an automatic promotion on the other. Our data is saved from being incorrectly rounded down, and the student receives their accurate, exact grade. This perfectly illustrates how explicit manual casting and implicit automatic promotion work together to preserve mathematical precision in everyday software development, preventing catastrophic rounding errors. This brings us to a very dangerous scenario. When you explicitly cast a larger type down to a smaller one, you face a severe risk of data loss, often called narrowing. Narrowing happens when the destination data type does not have enough memory space to hold the original value. The computer simply chops off the excess data. When casting between integer types, the higher order bits are completely truncated and deleted. This means the computer only keeps the lowest bits that fit, resulting in a completely different, seemingly random number. Let us visualize what happens during integer truncation. Here, we see a 16-bit integer being forced into an 8-bit character space. The computer does not round the number or try to find the closest fit. Instead, it literally cuts off the most significant bits, the upper 8 bits on the left, and throws them into the void. Only the lower 8 bits survive the transfer. This remaining binary sequence forms a new number that looks completely unrelated to your original value, causing silent data loss. Let us calculate the exact result of a dangerous narrowing cast. A programmer tries to store the integer value 258 into a character variable, which can only hold values up to 255 due to its small memory size. To see what happens, we must look at the binary representation. The number 258 requires more than 8 bits to be stored properly. In binary, it is represented as a 1 in the 256 position and a 1 in the 2 position. Here, we see the binary bits of our number. The rightmost 8 bits equal the decimal number 2. The 9th bit from the right is a 1, which represents the value 256. Because the character variable only has an 8-bit box, the computer ruthlessly chops off that 9th bit because it simply does not fit. It does not round the number or warn you about the problem. The higher order bits fall into the void and are deleted forever, leaving only a fragment behind. Only the lowest 8 bits survive the transfer. The final value stored in the character variable is just 2. The original value of 258 has been completely destroyed due to data overflow and truncation. This proves exactly why narrowing casts are highly dangerous if you do not verify the size of your data first. You must always ensure the destination memory space is large enough to hold the value. Otherwise, your software will suffer from severe security vulnerabilities and crashes. We have covered the critical mechanisms of type conversion. Remember, implicit promotion safely expands your data to preserve precision during math operations. However, explicit narrowing casts carry a severe risk of silent data loss and truncation. Always ensure your destination data type is large enough to hold the value you are pouring into it. Mastering these concepts ensures your statistical models and mathematical calculations remain perfectly accurate.